In the last lecture, we discussed the reflexive property of asymptotic notations. Now we will discuss the symmetric property of asymptotic notations. So let's get started and let's see the topics. The topic is asymptotic notation symmetric property. Let's understand what is the symmetric property first, and then we will prove that the symmetric property of asymptotic notations is true. So here is the symmetric property. If Fn is theta of Gn, then Gn is also theta of Fn. Symmetric property is applicable on theta notation. If we are saying that Fn is theta of Gn, this means if Gn is the tight bound of Fn, then Gn is also theta of Fn. This means Fn is also the tight bound of Gn. In other words, we can also say that if Fn is asymptotically equal to Gn, this is the meaning of theta notation. If Fn is asymptotically equal to Gn, then it makes sense to say that Gn is also asymptotically equal to Fn. That's what we are mentioning here. If Fn is asymptotically equal to Gn, then Gn is also asymptotically equal to Fn. So it does not matter whether we write Fn equal to theta of Gn or Gn equal to theta of Fn, they both are one and the same. Now let's visualize the symmetric property through the graph. Here is the graph for Fn equal to theta of Gn. We can observe here that Fn is sandwiched between C2 times Gn and C1 times Gn. We can observe that for some constant C2, Gn is acting as the upper bound of Fn, and for some constant C1, Gn is acting as the lower bound of Fn. So clearly Fn is theta of Gn. We already know the definition of theta notation, and from the definition also we can say Fn is less than or equal to C2 times Gn, but it is greater than or equal to C1 times Gn. So we can say that Fn is theta of Gn. This is from the definition of the theta notation. Now we know Fn is theta of Gn from this graph. Let's try to draw the graph for Gn equal to theta of Fn. Let's shift this graph over here, and here is the graph of Gn equal to theta of Fn. We can observe here for some constants C2 and C1, Fn can act as both the upper bound and the lower bound of Gn. This is what we can observe through this graph. After some n0, C2 times Fn is the upper bound of Gn. After some n0, C1 times Fn is the lower bound of Gn. So this is the graph of Gn equal to theta of Fn. From these two graphs, one thing is clear, that for some constants, Gn can act as upper and lower bound of Fn, and it is also possible for some constants C2 and C1, Fn can also act as both the upper bound and lower bound of Gn. So with this, one thing is clear, that if Fn is theta of Gn, if Fn is theta of Gn, then Gn can also be theta of Fn. Now let's try to prove this property mathematically. For this purpose, we will take a simple example and we will try to prove that this property is true. So let's take a simple example. Let Fn is 2n cube and Gn is n cube. So Fn and Gn are two functions where Fn is 2n cube and Gn is n cube. I am intentionally taking these two functions. These two functions have the same degree. This means the powers of n are the same. In this function, n is raised to the power 3, and here also n is raised to the power 3. The difference between these two functions is that n cube is multiplied by 2 in this function, and here n cube is multiplied by 1. Only constant difference is there, so we can say these functions are asymptotically equal. But how do we prove this mathematically? For this, we need to apply the definition of the theta notation. Let's try to prove that Fn is theta of Gn. This means Fn and Gn are asymptotically equal. According to the definition of the big theta notation, Fn is theta of Gn if and only if C1 times Gn is less than or equal to Fn and Fn is less than or equal to C2 times Gn for all values of n where n is greater than or equal to n naught and C1, C2 and n naught are constants. What is the meaning of this inequality? If we observe this inequality, here we have Fn less than or equal to C2 times Gn. This means C2 times Gn is the upper bound of Fn. This is what we observed in the graph as well. C2 times Gn is the upper bound of Fn and C1 times Gn is the lower bound of Fn because C1 times Gn is less than or equal to Fn. We have observed this in the graph also. C1 times Gn is acting as the lower bound and C2 times Gn is acting as the upper bound of Fn. So Gn is behaving as the upper and the lower bound of Fn. Now can we say this definition is true for these two functions as well? Fn is 2n cube and Gn is n cube. Can we say Fn is theta of Gn? Let's find out. Let's assume C1 and C2 are 1 and 3 respectively. Now let's replace C1 by 1, Gn by n cube, Fn by 2n cube and C2 by 3. We will get this inequality. N cube less than or equal to 2n cube less than or equal to 3n cube. Can we say this inequality is true? From this inequality we can observe that n cube is less than 2n cube and 3n cube is greater than 2n cube. So for some constants C1 and C2, Gn is acting as the upper bound and the lower bound of Fn. So we can say this inequality is true and hence we can say Fn, which is 2n cube, is theta of Gn, which is n cube. So it is clear that Fn is theta of Gn. This means Fn is asymptotically equal to Gn. As we can also observe here, these two functions are asymptotically equal. There is only constant difference between these two functions. I have chosen these two functions intentionally because we need to assume initially that Fn is theta of Gn. Then only we can show that Gn is also theta of Fn. This property holds good when Fn is theta of Gn first. If it is true, then we can show that Gn is theta of Fn. Now let's show whether Gn is theta of Fn or not. If we think logically, these two functions are asymptotically equal. So it does not matter whether we write Fn equal to theta of Gn or Gn equal to theta of Fn. They both mean the same. Both have the same meaning that Fn is asymptotically equal to Gn. Now let's try to prove this mathematically as well. Now the definition will also change. In place of Fn, we will have Gn everywhere, and in place of Gn, we have Fn everywhere. So the new definition will be Gn equal to theta of Fn if and only if C1 times Fn is less than or equal to Gn and Gn is less than or equal to C2 times Fn for all n greater than or equal to n naught where C1, C2 and n naught are constants. Now let us assume C1 is 1 by 2 and C2 is 1. Why have I chosen C1 as 1 by 2? I want to show that C1 times Fn is less than or equal to Gn. We know Fn is 2n cube. 2n cube is neither less than or equal to n cube. But if we multiply 2n cube by 1 by 2, we will get n cube here. So the inequality will be n cube less than or equal to n cube. N cube is not less than n cube, but n cube is equal to n cube. So the inequality is satisfied. And I have chosen C2 as 1 because n cube is already less than 2n cube. Hence this inequality is satisfied. So now if we replace C1 by 1 by 2 Fn by 2n cube, Gn by n cube, and C2 by 1, we will get n cube less than or equal to n cube less than or equal to 2n cube. This inequality is true because n cube is less than 2n cube and n cube is equal to n cube. Therefore, this inequality is true. And we can also observe that Gn is acting as both the upper bound and lower bound of Fn. Therefore, Gn is also theta of Fn, and hence we can say the symmetric property is satisfied. If Fn is theta of Gn, then Gn is also theta of Fn. From the graph also we have observed the same thing. We can sandwich Fn between Gn for some constants C1 and C2. In the same way we can sandwich Gn between Fn for some constants C1 and C2. Therefore, this symmetric property is satisfied. Also, please note that symmetric property is not applicable on big O and big omega. The reason is that if we are saying Fn is big O of Gn, this means if we are saying that Gn is asymptotically bigger than Fn, then how can we say that Fn will be asymptotically bigger than Gn? In the same way, symmetric property is not applicable for big omega notation. If we are saying Fn is big omega of Gn, this means Gn is asymptotically lesser than Fn. If we are saying that Gn is asymptotically lesser than Fn, then how can we say Fn is also asymptotically lesser than Gn? So symmetric property is not applicable on big O and big omega notations. I hope the reason behind this is completely clear. So with this we have understood the symmetric property of asymptotic notations. We understood that symmetric property is applicable on theta notation only. It is not applicable on big O and big omega. So with this we are done with this lecture. Thank you for watching this lecture. I will see you in the next one.